maybe I take like x and v here as well. So what we have is a dE I in x direction and v times ij plus ei of x times dE j. So that's the Leibniz property. And now we look at the definition. This one here is really nothing else than omega I j at the point x in the v direction. So that's the definition that is, it's over here. That's the definition of the connection forms. And now we use the same equation, but like with the opposite here. So like it doesn't matter on which side I take the inner product, it's symmetric. But then if I look, here we have the dE I with an I here, but here we have it with the j. So this is then the omega I x and v. So we get 0 equals omega ij and plus omega ji. So this follows that omega ji equals to omega ij with a minus sign. So skew symmetric. So it's skew symmetric in I and j. So we can think of write, like if you think of that as a matrix, omega ij, it has like essentially only three elements that are left. It's omega 1, 2, omega 1, 3, and omega 2, 3. And then 0 on the diagonal because of the skew symmetric, and then the off diagonal ones here are automatically determined by the skew symmetry. So in particular, only and omega 2, 3 are independent values. So you don't have to calculate, if I ask you, for example, to calculate the connection forms, you don't really have to start again like with omega ii, where like the diagonal. You already know that they are like have to be 0. So you only have to calculate these three elements in order to calculate the whole connection form. And that's very similar to, as I motivated, similar to the skew symmetricity over there. So what is the difference between like these connection forms and the skew symmetric matrix over there? Like there's two differences. So what are the two differences between this skew symmetric matrix and this matrix of connection forms? Like one is like very obvious, right? Like here we have like always a 0, while here that element might be non-zero. So that's like the first thing that you notice. And the second one is that these ones are like differential forms. So they have an argument, the v direction, that gives you the direction. Well, these ones are functions of t. These ones are one forms. And the reason comes from the fact that for the Frenet-Serre equations, I only have to worry about what happens in the direction of the curve. So there's only like one direction that I have to worry about. While here, these one forms record like how the frames changes in all possible directions. So the argument dv was the question, how does the frame changes if I slightly change from here to here. So that's I have like a possible different ways in which direction I can move. While up there, we only have like one direction where we can move, namely the tangent direction. And both of these things are like, can be explained, or are explained by the following result, which connects the following, that C be a unit speed curve, and assume that the curvature, the kappa, is greater than 0, so we can talk about the Frenet frame. And suppose that E1, E2, and E3 is a moving frame on R3, let's say for the such that the restriction to the curve C gives the Serre frame. So the picture is we have like a curve. That's the curve C, and then along that curve we have like the tangent vector. That gives us a certain vector field along the curve. But now I extend that to the whole of the space. So we, in some continuous way, we have now a vector field that happens when I restrict it to C, I get my tangent vector field. So that's like E1. And similarly, I have the normal vector field, which goes in the normal direction, and I also extend that to have a vector field at every point. So they change quite a bit, and the only requirement of the moving frame is that when I restrict it to C, I get the tangent vector and the normal vector and like the binormal vector back. So that's the idea. And once I have that, we have the following statement. Omega 1, 2 at a point C of t in the direction of t equals of kappa of t. Omega 1, 3 of C of t in the t direction 0, and omega free, C direction gives us tau. So that's the result. It's like these connection frames, they're like very general, and they record, for example, the changes in all direction. But now if I restricted the attention to in the tangent direction, I get a number, I get three numbers, essentially. And it turns out that one of them is kappa, is the curvature at the point here. The other one is the torsion at the point here. And then I get like one additional one, which is 0. So the proof is actually very simple, and I'll let you do that as a homework exercise. It's no wonder that there will be numbers here. So you only have to check that these numbers coincide with the numbers that you get that were defined in terms of the Frenet-Serre frame. But like maybe the only little bit like question is like, why do we get 0 here? So let me explain that. So what is this equation telling us is that the vector E1 at the point which is like corresponding on the curve, which is just t on the curve, restricted to the curve. It was E1 is like the tangent vector. Does not tip in the E3 direction. In the E3 direction, and E3 is B. And we already saw that this is the case, that T cannot tip in the B direction because we had a requirement that it's a unit speed curve. So for unit speed curves, the change of T is only in the n-tier plane. So it was only in this plane of the n and the t that like the t is changing. It never goes in the b direction. And that's consistent with this fact that omega 1,3 is telling us, like, if you look at t in the b direction, the change, it will never happen. Like, there will never be any contribution. So omega 1,3 t equals 0. So we'll never tip into the b. So, like, the important result of that statement here is that we can recover essentially a Frenet-Serre equation as a special case of the structure equations. So, like, these equations that we showed is like essentially equivalent under this identification in the t direction. It gives us immediately our Frenet-Serre equation back. And like the only input that we had was this essentially this sentence here. That we have a Frenet, like the moving frame is adapted to the curve in the sense that when we restrict it to the curve, we get t and then b back. But outside of the curve, it can do whatever it wants. We essentially don't care. And that same strategy will be like very helpful, like in order to study surfaces, where we can also say, okay, we want like a moving frame which is adapted to the surface in a certain sense that it restricts on the surface, say in a normal direction or something. So that will be discussed next week. But that's essentially the geometric ideas. Like the moving frame in itself gives us these omega ij's, and then we require that they are adapted to the geometry by having a sentence like that, and then we get, out of the omega ij's, we get the curvature or something over geometric that is important. So that's the idea. So in the remaining 50 minutes, I would like to discuss essentially a dual version of the structure iteration. And the insight or the idea is that the frame here, E1, E2, and E3 is not the most basic object, but the dual is more interesting. So instead of the base, like the frame in itself, it's like nice to look at like the opposite direction and look at the dual basis. So that's like essentially the same kind of information, but the dual happens to be nicer to work with. So let's define the dual frame. So what we have is like we have 3 one-forms. All of them are one-forms on R3, such that omega I, if I plug in the vector Ej, what I get is delta Ij. So 1 is I equals j and 0 otherwise. So these are one forms which have these defining property. And it's enough, of course, because to define these thetas on the basis, because these ones are a basis, so by linearity, it's enough to tell, let you know what they are defined. So that's essentially the example would be it's like one that we already saw. It's dy, dx, and dc for E1, the constant that points in the one direction. So for the constant ones, dx, dy, and dc are already like the dual frame that we already saw. But now the idea is to exactly more or less to exploit why these things were so important, and now is like to generalize them to the case where the frame was depending on the point and where the frame in itself was not constant. So these ones are called a dual frame. important property is that these that like omega ij, which are like the connection forms, are differential one forms, and these theta i's are also differential one forms. So now we have like a couple of objects, all of them are like one forms, and that's the main idea. And there might be some relationship between them, and that's what I want to do derive for the last few minutes. It's what is called Cartan's first structure equation. And it's again the similar trick. We first derive something that is constant, and then we take d of that constant to get a nice equation. So note that for all x, say like in an open subset where the frame was defined, we have that v that maps to the theta k on v k of x. This one is just the identity here. So this one is v again. The way we can do that is we have to check it for E1, E2, and E3. So E1, if you plug in E1, then theta only contribution would be where k is equal to 1, then this term is 1, and then we get E1 back. And similarly, we can do it for E2, then k has to be 2, and for v equals to E3, you have to plug in k equals to 3. So it's a function that like sends v to v itself back, using the dual basis as the important ingredient. Hence, it is constant. So this differential form, we get 0 if you take d of that differential form. That sends v to this vector. So this one gives us 0. And now we use our, so the way you should read that is that this is a one form and then times a vector. So it's not like the dot product, but it's like this one is a one form for every k. What we have is like this one is a one form, and then you get a number, and that number is scaled by the vector ek. So let's do our trick how to take the differential of a one form. So what we end up with is that we have to take, so we consider this one as a function. So that's for each coefficient it's a function. So we know that we can write this one as d ek which theta k plus d theta k. And then we have to take the sum over k. So we would now like to use the structure equation for this term. So we can write this as sum over k, the sum over I. So it's omega ki which omega k and then everything times ei plus d theta k dk. And now we see here we have the sum over EI, and here we have the sum over EK. So now it's the trick to take these inner sum and rename them so that we have the same, collect like all the same basis elements. So if I continue there, what we end up with is that we take the sum out of EIs. So we rename here the K to I so that we get the same element. So what we end up with is this sum here over K. So we have first term is the K omega Ki, and then the wedge product of theta K. And then in the second term we get d e theta, and now with the subscript I. And all of that was 0. That was the starting point. Like all of the things that we now derived was 0 because this function was constant and we took d of it. So EI is a basis, and you remember that like if you have a linear combination and you get 0 of a basis, that means that the summands in the basis have to be 0. So what we end up is the following equation. This one is 0. So that's what is called Cartan's structure equation. First one. And the important part here is that you can read that as a definition of omega. So what we did was now derive it from the definition of omega Ki as this inner product of d and the change. So that was a geometric thing. But now we can like read that equation essentially because theta k is like the dual basis. We can read this as the definition of the omega Ki. As an alternative. So the idea here is we start with a frame, but then actually we look only at the dual frame. So now we pose the dual frame as the fundamental object. That's a one form, or actually 3 one forms that someone gave to us. Then we take d of these one forms to get like some expression, and then we write these equations that we get in terms of certain other one forms times wedge product of the original frame that we had. And whatever we have to put in here gives us a certain certain coefficients, and if we require that they are anti-symmetric, then they are uniquely defined. And that gives us like an alternative way to calculate these coefficients. So that's the first structure equation of Cartan. And there's a second structure equation. second structure equation is following that what we saw last time is equals to 0 for all functions. So if you take d of f, you get a differential 1 form, and then you take like the d again, you get a 2 form, but that 2 form always was 0. That we saw last time. So let's apply this equation, but instead of f, we consider E1 or E2 and E3. So what we end up with is that here that the d of E1 was these 1 forms that we discussed earlier, and then we take d of that again, and we get 0. Just by the definition of d, which was saying we take the components and then we apply it in each component. So we now apply this function in each component. So we get 0. So let's see what happens if you plug in the definition of E1 here. So what we end up with is that it's the inner product, if I write it a little bit symbolic, of these omega ij's times eg, to take the d of that, we get 0. So now let's do that and see what happens. So we treat these ones again as a function. So what we end up with is that it's d e ij, wedge product of the omega ij. Some plus, and now we use the plug in the omega ij. We get 0. And now here we can plug in the same equations again, the structure equation, to write it as dj dk omega jk dk wedge omega ij. And here I don't change anything. And now we do the same trick where we bring out the ek by like just changing the summation. And what we get is the following equation. Omega jk wedge product omega ij plus d omega ik equals to 0. So you have these structure equations as connection forms. You take d of that and you calculate it, and what you always get is that it's these funny looking like wedge product of the connection forms again. So that's the second structure equation. So there are like 2 remarks. The first one is, and that's something that we will see next time, is that this 0 here, we have 0 here, is essentially expressing that we were working the whole time in R3, which is like flat space. So that's expressing flatness of R3. So what will happen is that if you look at like the same kind of ideas and but not on something like on R3, but like a more general, like some curved surface, what you get is something that will be non-zero, and that exactly will be the measuring of the curvature. So you calculate this side, you calculate this side, and it will be, normally it will be not zero, but something else, and that something else gives you then the curvature. So that will be like a preview. The teaser for next time is like we will look essentially on the right-hand side and like study that to define the curvature. So that's the first remark, that this zero is like expressing the flatness. And like the general philosophy here is now the following: is we start with these three one forms. We essentially forget that they have to be a dual frame. They can be more or less like arbitrary. So that's like the first thing that we give ourselves. Then we take d of these one forms and write it as an equation of this form to define the connection forms. Once we have the connection forms, we use this equation, the second structure equation, calculate d of the connection forms and calculating the sketch product of these forms, and then check if that's zero or not, to define, like, to look at like the curvature of the object that we look at. So that's the general philosophy. How we now get something like from these one forms to connection forms, and then like to the curvature. So that's the general idea. And for the last few minutes, I would like to make a bit like advertisement for why that idea is like so cool and so powerful. Namely, the point is that it essentially doesn't make any reference to three dimensions anymore. Like all of these things are like certain sums, and it would make sense, completely sense, to look at like these things in 2 dimensions, in 3 dimensions, and then 4, and then 5, and so on. So it's like a very general procedure that works in arbitrary dimensions, while it's not clear, for example, what it would mean for like a 2-dimensional object to have a frame that is adapted in 5 dimensions. Which kind of like coordinates do you choose in which directions, or what kind of like relationship you need. But these equations are very universal and make sense in arbitrary dimensions. And there's like a few ideas, namely that they also encode the geometry in some ways. So what we already saw is that if you take like skew symmetric omega ij, so if they are skew symmetric, then it's essentially related to the Euclidean geometry. So the skew symmetricity we derived by just taking the orthonormal basis condition. And that was, of course, relative to that we have like the Euclidean inner product. If you would have like a different kind of geometry, say hyperbolic, or like you take a different inner product, then you would like get like a different kind of symmetry or like some kind of construction there. So the skew symmetricity of these matrices are related to like what kind of geometry you look at. And just like some advertisement here, if you, for example, in 4 dimensions, look at like certain things which are skew symmetric in a few elements, but then symmetric in a few others. So here it's really not a typo that the minus sign is not missing. So if you say that omega ij has to have this form in 4 dimensions, then it gives you the Minkowski geometry, which is the geometry of general relativity. So that's a certain kind of geometry that is adapted to the speed of light, if you want. And that just follows by taking a certain or putting requirements on the omega ij's, which are saying they don't have to be a skew symmetric, but they have to be a symmetric in certain indices and skew symmetric in other indices. And that gives you directly like a different kind of geometry and different kind of physics. And then there was a really huge insight, and it was like about 40 years ago, that if you take just some other matrices, for example, we can require them to be like 2-dimensional objects which have for example trace 0. So if that's omega ij, then it's not related to things like gravity, but some other elementary forces. And for example, this part choose here is related to electromagnetism. So something that you might have not imagined at the beginning is our beginning was really motivated by, let's look at frames and how they change, and that we record in these connection forms. But now it's really just okay, they are skew symmetric, and that reflects the geometry. Let's play around with only the skew symmetricity, and then you realize that some property like electromagnetism can be recovered or implemented by saying that these matrices have to be trace 0 and 2-dimensional, for example. And there's many other models where we now change essentially the requirements of the matrices. And then we get the whole particle sewer of the standard model. So that's it's an observation that goes back to Yang-Mills theory, which would be way too much. But just as an explanation of where if you want to study further differential geometry, one way it would be understand these sentences a bit more in detail. How is the geometry and how are forces encoded in the different choices of omega. But yeah, I think for this course it will be enough as a teaser, and we will focus next time on the geometry again. So see you guys next week. Yes. The same idea is that I should It's like always like you want to do it. Yes, you can see them as like it's a dot product. Yes, yeah, that's true. Yes. What it is, like essentially yeah, it's yeah, I think it will go too far if I would not explain how electromagnetic is like really. But the idea is really that eventually you have like, I think like the best way to think of that is like TIA equals electromagnetic field and minus electromagnetic. It's not really the best way to think of it. So it's like the same kind of information. There's like this one is a one form, and then you require it to be like this one to be zero. So it's only one form that is enough. And that one form is related to mostly like we have like what we say like you require it to be like a different kind of and then you have like some general relativity. So if you're interested in that, I would really recommend like some geometric things to general which really go into much stuff. And in some way, like this young theory is like particle physics. So that's like really a thing, like the fundamental forces that they like elementary particles. Like at the super EI, and then that's like and these ones are really interesting. That in that case, these ones will be like the transmittance of the yeah, so in electromagnetism, it's like the photon. You get a particle that is like essentially short with different particles. So it's like here's some light, and like the pressure that you get by sending light or so that's the photon, and the photon is essentially in this theory, like we have different kind of also like asymmetric versions, and then you get like multiple like elements, and all of them linear combinations of them. That's like some geometric idea that they are like some like gluons. So that's like one explanation. in the sense of we have to think as we move. Like a divergence. So that's like the next one. And this one here, you can think of that, like, essentially it's differential geometry here. And then this F here, essentially you can think of that as like the structure equation. So it's like the F that you know from electromagnetic you can put them in a one like a bit more intelligent. And then what you get is the structure equation. So this is really like and then this equation here is really just like translated into the structure equation.
What is the unit in?
That's like essentially like if we think of like these ones as these ones happen to be zero. Like the wedge product of these ones vanish because of some symmetry conditions. That is like they're kind of like cut off. And then what you get is the and that's like So that's like what I mean. Here it's like Euclidean geometry. So you say like Euclidean, and you get like but this one is so Euclidean geometry. Of course, there's no. This one is like next to it. There's no Euclidean geometry. So that's why you have like. So it's like there's like a different kind of geometry. So that's why we don't have like so you I think I will put like a homework exercise where I guide you how you can like devise like Maxwell equations in how you do it.